Hi everyone, my name is Chen, and I'm excited to share our work on Can Domain Experts Rely on AI Appropriately, a case study on AI-assisted prostate cancer MRI diagnosis. So let's get started. There's been growing interest in using powerful AI models to help people make better decisions, especially in high-stake domains. In these settings, full automation isn't always the goal. Instead, AI is often designed to assist human experts, supporting their decision-making rather than replacing human experts. And this brings us the key idea of this work, complementary performance, not just asking who performs better, but exploring how human and AI can work together to achieve an even better outcomes than either alone. However, there is a significant gap in current human AI research. Experimental studies involving actual domain experts are extremely rare. Most of what we know comes from experiments with crowd workers on relatively simple tasks, but we don't know if the results we draw from those crowd worker studies can still hold up when applied to real experts' tasks. So to help close the gap, our work focuses on a real-world high-stakes domain, prostate MRI diagnosis. Prostate cancer is a very important problem. According to the NIH data, about 1 in 8 men will be diagnosed with prostate cancer at some point of life. Prostate cancer has been notoriously challenging for human radiologists to diagnose from MRI scans. According to the literature, the human radiologist can only achieve an AUC of 0.58. So we trained our AI model from scratch, and the AI model achieves an AUC of 0.80. So to start, we designed our first study, which is a very simple pipeline to measure 3 things: based on human performance, AI performance, and how humans perform with AI assistance. We recruited 8 board-certified radiologists and asked each of them to review 75 cases. And for each case, human radiologists went through a 3-step process. First, they made an initial independent diagnosis. This gave us the human baseline performance. And next, we showed them AI's prediction. As a final step, they have a chance to modify their own decision after reviewing AI decisions. And the final decision reflects the AI-assisted performance. And we are curious about these 3 performances. Before I show you our results, let's talk about the metrics first. So instead of traditional metrics such as accuracy or AUC, we wanted something more flexible, something that better captures the real-world cost of different kinds of error. And that's where V-shaped scoring rule comes in. And this scoring rule has a parameter mu that controls how harshly we want to penalize false positives versus false negatives. Intuitively, when mu is equal to 0.5, this scoring rule collapses to accuracy, and mu more equal to 0 or 1, it prioritizes sensitivity and specificity respectively. Now, let's talk about the results. In summary, we didn't observe any complementarity. And there's a consistent performance order of human alone performs the lowest, followed by human plus AI, and AI performs the best. Given these results, we hypothesized that radiologists charge their own training more than AI assistants, despite AI's better performance. And this highlights an issue of under-reliance. And now the question is, how can we promote appropriate reliance in human AI decision-making? So we want to nudge humans towards rely on and trust AI decisions more. That's why we consider human performance feedback and upfront AI assistance as intervention in our study too. And essentially, our goal is to communicate more information to human participants, and we hope that this can support them in making better decisions. And specifically, by performance feedback, we meant we will tell the human participants what their accuracy, sensitivity, specificity, and various metrics compare with AI's performance, and compare their performance before AI and after AI. So this gives us our study 2. After a minimum of 30-day washout period, we moved to study 2 with the same group of 8 radiologists. This time, each radiologist reviewed 100 cases. We include 50 cases that they had seen before from study 1 and added 15 new cases. we changed workflow in study 2. First, we provide them with performance feedback from study 1 so they could see how they did across various metrics, and then for each case in study 2, we simplified the process. They immediately saw the AI's prediction upfront and made one final diagnosis based on that. Alright, let's break down our results. In summary, we still didn't find any complementarity. Instead, we see a clear pattern in performance. Human alone performs the lowest, followed by human plus AI in study 1, then human plus AI in study 2, and finally, AI alone performs the best. And the key question now is there any hope that we can achieve complementary performance? And now let's take a look at theoretical complementarity. We adopted a decision theoretical framework from Jiamin et al.'s work 2024. So this framework provides a very nice theoretical definition of the best attainable performance. Essentially, given both human decisions and the AI's decision, the best attainable decision would be one that maximizes the expected return based on any defined scoring rule. And does this optimal strategy lead to complementarity? The answer is yes. Let's take a look at this density plot figure. On the x-axis, we have the score, and the first row shows the common trials, human alone performance, AI performance, and the best attainable performance. The second row represents the results from study 1, and the third row represents results from study 2. Let's take a look at the first row first. And this plot is from one scoring rule, mu equal to 1. But it's important to note that the pattern I'm gonna talk about later is consistent across all scoring rules. To interpret this image of the first row specifically, yellow represents human alone performance, and blue represents AI performance, pink represents the best attainable performance we discussed earlier. And it's very clear from the figure that pink curve is higher than both the blue and yellow, indicating the best attainable performance surpasses both AI and human performance. So that's really exciting. We have a theoretical best attainable performance, but what exactly are these optimal strategies, and can we provide them as tangible recommendations to our doctors? And the answer is also yes. And this table here shows the actual best attainable benchmark strategies. Each row here represents a different scoring rule. Interestingly, for most of the scoring rules, the optimal strategy turns out to be quite simple. So the strategy is you should only predict a patient case as a positive case when both the human and the AI agree that it is indeed a positive case. We have more results in our paper, but this wraps up our study, and I want to highlight our 3 findings. First, we observed a consistent performance order with secondly, performance feedback, our design intervention, performance feedback, and upfront AI assistance do nudge human towards rely on AI more. However, thirdly, despite improved reliance, radiologists still under-rely on AI compared to the best attainable performance, and they fail to rely on AI appropriately. And lastly, this is also what differentiates our work from all the previous works, we have extracted tangible recommendations for doctors to achieve complementary performance. And that concludes my presentation. Thank you so much.